Okay, let's go over this other exam, the uh, exam from spring of 2019, and go through the answers to that exam. We we start with this simple collision problem. This is just the standard collision problem, and I'll remind you from our last review session that we always go through this little decision tree. For every problem we ask, is this a collision? If so, we conserve momentum. If it's not a collision, we ask, is time involved? If yes, then we have to use the general impulse momentum equation, where the impulse is the force times the time, and that's what changes the momentum. If time's not involved and it's not a collision, then it's an energy problem, and we always start with this Kinetic energy equation right here. And then the energy can either be kinetic energy, which is 1/2 mv squared, or gravitational energy, which is mgh, or spring energy, which is 1/2 k delta s squared. And remember, those formulas are not going to be on the exam. As I said in the lectures, you're expected to have those memorized. So this is a collision problem, so we definitely want to start with P initial is equal to P final for the system. And because that's a vector equation, we're going to need a coordinate system. We're going to choose to the right to be positive, to the left to be negative. Oops, I'm sorry. Let me adjust that a little bit. Okay. Now, initially, I have a 5 kilogram block moving at 10 meters per second, and it's moving to the right, so that'll be positive momentum. I have a 15 kilogram block moving at 6 meters per second, and that's moving to the left, so that's negative. Then the collision happens. That's that equal sign right there. And afterwards, we're told that the small block bounces back with a velocity of 5 meters per second. So that's going to be 5 kilograms times 5 meters per second. It's bouncing back to the left, so that would be negative momentum. And then we have the 15 kilogram block, but we don't know how it's moving. That's what we're looking for. So we make that final velocity a positive variable. If I solve for that variable and I get a negative number, I know it's going to the left. So this is going to be 50 franci minus 90 franci is equal to negative 25 franci plus 15 kilograms times V final. Now, that's just algebra. I mean, that's just solved for V final. And if I solve that, I get V final is equal to minus 1 meter per second. I can either write it as minus 1 meter per second, or I can write it as 1 meter per second left. But I have to choose either this or that. Okay? Now, in this next part, we suppose that the two blocks stuck together. Well, the left side of this equation would still be true. I would still have, my P initial would still be 50 franci for the little block and negative 90 franci for the big block. But afterwards, if they stick together, I can treat them as one unit of mass 20 kilograms, moving at some V final. And if I solve for that, what I get is that V final in this collision is going to be a negative 2 meters per second, or 2 meters per second to the left. Now, we want to know how much energy is going to be lost in this collision. So let's look at how much energy we had before the collision. We had the 5 kilogram block moving at 10 meters per second squared. and we had the 15 kilogram block moving at 6 meters per second squared. Notice I didn't put a minus sign here because I'm squaring it. The minus sign is going to go away anyway. Okay, and that turns out to be 520 joules. The final kinetic energy, since they're all moving together, I can treat them as one unit of 20 kilograms moving at 2 meters per second. Again, I don't have to put the minus sign in there because I'm squaring that. And that's just going to give me 40 joules. Well, the change in kinetic energy is the final minus the initial. Well, that's going to be 520 joules minus, whoa, no. My bad. That's going to be 40 joules minus 520 joules, or negative 480 joules. So that means that 480 joules are lost in that problem. Okay. In problem 2, we have a 6 kilogram block sliding across a rough section of floor and gradually coming to a halt. And we want to know if it stops in 4 seconds, what's the coefficient of kinetic friction between the block and the floor? So initially I've got this block, and it has a mass of 6 kilograms, and it's moving at 12 meters per second. And it goes over this rough section for a delta t of 4 seconds. And we want to know what's mu sub k. Well, because time is involved and there's no collision here, this would be the general impulse momentum equation. If I choose to the right to be the positive x direction, then I start with positive momentum of 6 kilograms times 12 meters per second. And the force that's changing that momentum is going to be the friction force, kinetic friction by the floor on the block. And because that's pointing to the left, let me draw a free body diagram for the block. The weight of the block is going to be 60 newtons. That means the normal by the table on the block is going to be 60 newtons. And this friction force is going to be pointing to the left, and it's going to be mu sub k times the normal force. So because it's pointing to the left, I can make that negative. My time is going to be 4 seconds. And when it comes to a halt, it has no momentum. Now, if I solve that for the friction force, I get that friction force is going to be 18 newtons. Well, I also know that that friction force of 18 newtons can be written as mu sub k times the normal force of 60 newtons. And that is going to give me a mu sub k of 0.3. Now in this case, part B, we're told that instead we get it started a little faster at 15 meters per second, and we want to know how far would the block slide. Well, this is not a collision, and it doesn't involve time, so this is energy. Energy initial plus work done by the friction is going to be energy final. Because everything stays on the floor and there's no springs in this problem, by energy we mean kinetic energy. That's going to be initially 1/2 times 6 kilograms times 15 meters per second squared. The friction force, we said up here, was 18 newtons, and because it's acting opposite the motion, delta x, we can put a minus sign in here for the work. And when it comes to rest, there's no kinetic energy. And that gives me a delta x of 37.5 meters. Okay. In this problem, we have three cars, A, B, and C. A is going south, B is going west, and C is going north. And we're going to choose the standard coordinate system. And in that coordinate system, I can write the momentum of these three cars before the collision, and the momentum of the mangled cars. They come together, collide, and lock bumpers to become one single ugly vehicle with a dozen wheels. And we find that right after the collision, they're moving with this final velocity of 15 meters per second, about 30 miles an hour, in a direction that's 37 degrees south of west. Now, the kinetic energy of the mangled 3-in-1 car just after the collision, that's a really easy problem. Kinetic energy is just going to be 1/2 mv squared. So that's going to be 1/2 times the mass. And in this case, I've got a total mass of I've got a total mass of 800 kilograms, and they're moving at 15 meters per second. Got to square that, and that's going to give me 90,000 joules. If the cars skid after the collision for a distance of 18 meters, what's the coefficient of kinetic friction between the tires and the road? Well, we're dealing with a distance here, not a time, so that's an energy problem. Energy initial plus Werk external is equal to energy final. The initial energy is just this, we said this was the final energy after the collision, but now it's going to be the initial energy before the slide, at the beginning of the slide. So that's going to be my 90,000 joules. My friction force is going to act by the road on the cars, is going to act for a distance of 18 meters, and that's going to bring it all to a halt. Well, that means that my friction force by the road on the cars has to be 90,000 joules divided by 18 meters, and that's going to be equal to 5,000 newtons. Well, I know that the friction force, it's the kinetic friction by the road on the cars, and that's just mu sub k times the normal force by the road on the cars. Well, that means that mu sub k is going to be the friction force divided by the normal force. That's 5,000 newtons divided by 8,000 newtons, and that's going to be 0.625 or 5/8. The total momentum of the three-car system, well, it turns out that in a collision, any collision, if I include all of the things that collide, all of the things that interact, I know that the momentum is conserved. Okay? And for the system, and they're asking for the momentum of the total system before the collision, but that's the same as the momentum after the collision. And I can find the momentum after the collision. That's just going to be equal to total mass, 800 kilograms, times the velocity, 15 meters per second, at 37 degrees south of west. Well, that's going to be a total of 12,000 franci at 37 degrees south of west. Now, if I take that, I'm going to move over here. If I take that 12,000 franci and I break it up into its x part and its y part, if that's 37 degrees, then what I have is a 3, 4, 5 triangle. Okay, and so what I can find then is that this x part is going to be 9,600 franci, and the y part is going to be 7,200 franci. This is just going to be 12,000 franci times the cosine of 37 degrees. And this is going to be 12,000 franci times the sine of 37 degrees. Okay? Now, if I make a table of the x part and the y part of the momentum of these cars, well, car A, if you look at car A, it's all going in the negative y direction. So there I've got negative 200 kilograms times its speed. I'm going to make that a positive quantity. I've already got the minus sign here to say it's going in the negative direction. And it's got no momentum in the x direction. If I look at B, it's got momentum in the negative x direction, negative 400 kilograms times VB. And again, VB is going to be a positive quantity, a speed, because I've already got the minus sign out here. It's got no momentum in the y direction. And if I look at C, it has no momentum in the x direction. It's all in the positive y direction, 200 kilograms times VC. And VC is a positive speed. Now, I don't know what these things are because I don't know those speeds, but I do know that they've got to add up to the total momentum for the system. And the total momentum of the system, the x part is going to the left. So, okay, let's see if I can make this all show up here. It's all going to the left, and that's a negative 9,600 franci. And this y part is all going down, so that's a negative 7,200 franci. Well, that gives us the information we need to solve parts D and E of this problem. If I want to find the initial speed of car B, well, that's this right here. And I know that this column here has to add up to the total for the x direction. So that gives me that minus 400 kilograms times the speed VB is equal to minus 9,600 franci. Well, that gives me a VB of 24 meters per second. So that's the speed of the car before the collision. Now, if I want to know how much faster car A is going than car C, what I'm looking for is VA minus VC. Right? That would be the difference in their speeds. Well, that I'm going to get by adding up this y column. If I add up that y column, I get minus 200 kilograms times VA plus 200 kilograms times VC is equal to minus 7,200 200 Franci. Well, if I pull out a negative 200 kilograms from each of these terms, I'm going to get a VA here, and I'm going to get a minus VC here. Everyone see how I did that? Oh, no, you didn't, because it was below the screen here. Negative 200 times VA gives me negative 200 times VA. Negative 200 times negative VC, the negative and the negative cancel, and I get a positive 200 VC. So this is the same as this. Okay? Well, now I can solve for what I'm interested in. VA minus VC is just going to be negative 7,200 Franci divided by negative 200 kilograms, or that's going to be 36 meters per second. So I don't know how fast car C is going, but I know that car A is going 36 meters per second faster. So if C's going 10 meters per second, A's going 46 meters per second. That's what I know. Okay. Now, this problem here, I worked in all of its gory detail. I did that in the Monday lecture, the Monday before the exam. And so I worked that on the board in the lecture, and it's there for you to go and see. I've only got a few moments before my office hours start. So let's look at the multiple choice. We have this situation where a 10 kilogram red block slides to the right at 3 meters per second, and it collides with a 10 kilogram block, blue one, going to the left at 5 meters per second. After the collision, the red block's moving at 5 and the blue block's moving at 3. It turns out that the initial kinetic energy is just going to be 1/2 times the 10 kilograms for the red block times its speed of 3 meters per second squared, plus 1/2 times the 10 kilograms for the blue block and its 5 meters per second squared. And that gives me 170 joules. If I do the same thing for after the collision, well, now the red block is moving 5 meters per second, and the blue block is moving at 3. And so I still get 170 joules. And so since the kinetic energy initial is equal to the kinetic energy final, that's elastic collision. Now, a Newton meter is equal to a joule. And if I divide that by a second, that's a joule by a second, and that's the definition of a watt. And so this is going to be E. Here, I know that power, if something's moving at a constant speed, is just the force applied times that speed. So here I have 1,000 watts, and that's equal to the tension force, that's the force, times the speed of 5 meters per second, and that gives me a tension force of 200. A fly is going east when it collides with a windshield of a car going west. Not a good day for the fly. Which two phrases make the following statement true? The force the fly exerts on the windshield is equal to the force the windshield exerts by the fly. Therefore, momentum is conserved. So that's going to be A. I have a 6 kilogram block moving to the left on a frictionless table. A hand pushes on the block with a constant force of 20 newtons to the left for 3 seconds, 10 newtons to the right for 6 seconds. So let's set up a coordinate system. Let's call to the right positive x and to the left negative x. Well, I've got P initial plus my force delta T is equal to P final. Well, in this case, my force delta T is going to be two parts. I've got a negative 20 Newton force acting for 3 seconds, and I have a positive 10 Newton force acting for 6 seconds, and that all adds up to 0. And so if that's 0, then there's going to be no change in my momentum. Okay. I'm going to have to end this here because my office hours are starting, or should have started a couple of minutes ago, and so you've got the written solutions to these on D2L. I hope this was helpful. Ta-ta.